My name is Geir Norden. I'm from Norway. I'm a Master of Science from Civil Engineering in NTNU in Trondheim. I've been working in the Leka company for about 30 years, and I joined, our company joined Saint-Gobain in 16, 17 years ago. So my role in the company is mostly R&D and technical support, and I cover all our fields, including Filtralite. Typical tasks that I do is to develop new products. I have all the contacts with the institutes and universities, and typically optimizing Filtralite product and production process and filtration process. I'm in regular contact with clients as a sidekick for our salespeople, like Mohammed. So I'm the one that, if you want to have a meeting with us, I'm very often a part of those meetings together with Mohammed. So, like Mohammed just have explained, the Filtralite is a ceramic material, which is heated up to 1200 degrees, followed by crushing and sieving. And the grain size for typical biofiltration is usually between 0.8 and 5 millimeters, and we usually select a bulk density of 800 to 900 kilo per cubic meter dry material for biofiltration. Please also add that since this is a porous material, it needs soaking. And
excuse me, Geir. I don't know if you know that you're not sharing right now. Did you want to be sharing your screen?
I'm not sharing. My computer said that I'm actually is sharing.
Maybe you can try.
Can you see me now?
Not yet.
Well, my computer say share. Let's see if I can share again.
Okay.
Yes.
No, you can see me.
Yes.
Now you're sharing.
Sorry, what happened?
No, sorry. My mistake.
Okay,
now,
I continue. Okay, I continue. Okay, as I said, the Filtralite, since it is a porous ceramic material, it will the soaking will impact the density, and this is important to understand, and we therefore recommend soaking. The highly porous structure with the huge surface area, it's more than 1500 square meter per cubic meter, which makes this material a perfect material for as a carrier of biofilm. As also Mohammed said, this irregular shape and uniform size, it results in high woods volume, so you can store a lot of biofilm as sludge, giving a very long filtration runs. And it also results in a very high attrition resistance, mentioned by Mohammed. The thing is that we can make tailor-made materials perfectly for all types of wastewater and drinking water filtration system, both biofiltration and filtration. So when we come to this filtration in wastewater, it's mainly two processes. It's what we call biofiltration, and it's granular filtration, which also often is referred to as retention filtration. And we have made some sketches here to illustrate how it's done, but let me instead use words. When it comes to biofiltration, it is typically nitrogen removal. That is the main topic, and we have been delivering this material for 30 years, and it is typically a removal of ammonia from wastewater. That is the biggest topic. Of course, there is also question about if it removes BOD, which is biological oxygen demand, or ammonia from drinking water, and sometimes manganese and iron. But the biggest area for our use is in nitrification and denitrification. When it comes to granular filtration in wastewater, it's typical tertiary filtration. That means that the filter is added in the end of a process for a final filtration, either as a monofilter or as a dual filter. And then the filtralite function for wastewater, as it does for drinking water, it simply has the role of attracting grains and keeping them in the filter until it is backwashed. So this is a typical model of a biofiltration. It's typical, not always, but very typical, that the raw water is coming from the bottom and is generating an upstream system. And it's also typical that it's a monofilter and not a dual media filter for biofiltration. So the bacteria then are making a biofilm and are responsible for the biological treatment. These bacteria, they occur naturally in the wastewater, and what we do with the filter material is just to make a perfect condition for them to grow and develop. Biological treatment of ammonia, it's done in 2 steps, nitrification and denitrification. And when the bacteria has consumed ammonia or whatever it wants to remove, it will continue to grow as a large biofilm, which is backwashed regularly. The typical process for removing of ammonia, it's a dual process. It's both nitrification and denitrification. And the nitrification takes place in large aerated filters, which is filled then with a filtralite, typically a filtralite called HC 2.5 to 5 with a very large surface area. And in step 1, we can see that the ammonia is consuming oxygen and generating what we call nitrate. And the second step of nitrification is to take the nitrate from nitrate to nitrate, again consuming oxygen. And what is important to notice here is that this process is consuming rather much oxygen. Actually, 1 gram with ammonia consume about 4.5 gram oxygen. And this is the reason that nitrogen removal has been so important, at least in our world, in Europe, for several decades. It is that the nitrogen in the form of ammonia consume oxygen, and this is a problem for the recipient. The excess biofilm is removed by backwash, and it's very important to note here that when you backwash a such filter, then the biofilm is still attached to this porous surface. So what you actually remove is only the excess sludge, the excess biofilm. So I said that 1 gram of ammonia remove 4.5 gram of oxygen. In this case, I just show you a typical Norwegian average wastewater. And you see that when you have 30 gram with nitrogen, where most of it is ammonia, and you have a consume of 4.5 gram oxygen per gram ammonia, it contributes a lot to the total biological oxygen demand. Actually, so much that if you want to handle oxygen demand, you actually need to remove nitrogen. The second phase of the process is denitrification, and then you take the nitrate and remove it to nitrogen gas. And this takes place in a second reactor where you have less oxygen available. And as same here is that the excess biofilm will be removed by backwash, and new biofilm will be created on the surface of the aggregate. So it's a 2-step process. One is aerated, the second is not aerated, and the second one we typically use a filtrate called HR 3 to 6 or HR 4 to 8. One example. The first plant actually we supplied to was in Oslo. That was the beginning of the filtralite. It's 30 years ago. And it was used, the 2 products that I mentioned, they were actually developed back in 30 years ago for this specific process. And this process has been existing now for 30 years. It's still fully operational. The filter material is still functioning in the filter. It's not been replaced. Of course, we have added a little bit because you lose some over the years, but not very much. In this process, they have first chemical precipitation, flocculation, and sedimentation system, where you remove a lot of the organic carbon, suspended solid, and phosphorus. So when the water comes to these biofor aerated tanks, then we have a ammonia level of, in this special case, of about 17 milligram per liter. And we see here during the depth of the biofor process, it is removed. And down to 2.8 meter, we have reduced the ammonia content from 17 and down to about 3 milligram per liter, and even further down to 4 meter. Interesting to see is also here it's measured as TOC, that you have the same reduction for organic carbon together with the nitrogen in the same reactor. Also note that the pH is falling through the system, which is important to consider when you are designing a such system. Another case study in Dalian, we have a requirement of BOD5. Here we have used Filtralite, and I think it was 2.5 to 5 HC. Requirement was less than 10 microgram per liter on BOD5, and we achieved actually 3. COD less than 4, we achieved 30. Suspended solid requirement was 10, we achieved 8. And ammonia requirement less than 5, and we achieved 1.5. And you see the inlet figures in this column. In total, 12 filters for BOD, COD, and suspended solid removal, and 12 filters for nitrification. Another case here. In this case, we are supposed to remove a TOC, and comparing Filtralite, monomulti, and anthracite sand at 2 different velocities. At 5 meter per hour, the Filtralite removes, in this specific case, 50%, while anthracite and sand remove 37%. But if you look at a triple velocity, water velocity, increasing the velocity from 5 meter per hour to 15 meter per hour, you see that the Filtralite monomulti is still performing very well, while the other solution with anthracite and sand is not performing that good anymore. In this case, we are comparing monomulti and sand. It's the same case, but it's the head loss buildup for 5, 10, and 15 meter per hour. And we see that the the head loss buildup for sand is considerably higher than for Filtralite, particularly at the high volume, high velocities. Next step, and here I have a little problem that I cannot remove the headline from my presentation, the Zoom headline, but I will try to take it anyway. In this case, in this situation, we are going to remove iron, ammonia, and manganese, typically from drinking water, and this can be done in the same reactor under specific conditions. And it's 3 different chemical reactions. Iron is removed from iron 2+ via oxygen to iron 2 oxygen G, which is very similar to rust. And this is a oxidation, precipitation, and filtration reaction. That means that on the surface of the filter material, you will have oxidation of iron. Then it will occur precipitation, and this precipitation, a precipitated product, will later be filtrated in the same filter system. Ammonia, as said, it is removed by bacteria and oxygen. which is called biofiltration nitrification. And manganese removal is a much more complicated reaction. It is a autocatalytic manganese oxidation, which is a kind of a bioprocess. So it's a kind of biofiltration process that goes through several steps. And what is important for those steps is that you need to absorb some of the manganese on the surface and generate biofiltration and a biofilm for biofiltration. So in a typical downstream system, it is essential to assure that the iron removal layer is as short as possible from top of the filter media. This is because that iron and ammonia need to be removed before the manganese process start. That also requires a rather deep bed, because you first need to remove iron and ammonia before you can start with the manganese. The necessary conditions for manganese removal in a combined system is that there is sufficient aeration of raw water. Oxygen is needed for a second step of the oxidation mechanism. Effective removal of iron prior to manganese removal. Development of the catalytic layer in the natural working method. Elimination of disinfectants in the natural working method because of working of the bioprocess. Ensuring optimal pH. It has to be above 7, and regular backwash. And the condition for nitrification are that the raw water needs aeration. It needs quite much oxygen. Temperature should be above 4 degrees, which I don't think is a problem in the Middle East, and preferable a pH of 7.75. So we have an example here from Poland, Nentech in Poland, and they did a really good study on a combined removal of iron, ammonia, and manganese in the same reactor. And if you look at the gray, I hope it's gray on your screen as well, but the gray line, you see that the iron starts on 1.6, and it reaches the actual limit for iron here at 0. This is the depth of the reactor, and you see that the iron is removed down to the expected value or the critical value after only 40 centimeter. If you look at ammonia, it is more or less the same. It's the green line. It is removed to the expectation of about 30 centimeter from the bottom. The rest of the volume in the filter reactor is used for removing manganese that needs a lot of more space. What happens with manganese is that already after 20 centimeters you have some reduction, but then it takes a rather long distance in the filter, so it needs a rather large filter volume before it reacts completely. And first after 2.8 meter depth, the manganese is removed. So what this tells us is that it's fully possible to remove both ammonia, iron, and manganese in the same reactor, but the reactor needs to be rather deep to manage this. This is a case study together with Acciona, and in this case we had to remove high ammonia content in the drinking water site, reduce OPEX, and ammonia peaks up to 7 ppm. It was done in a biological aerated filter system. The filtration speed was from 10 to 12 meters per hour. Inlet water was between 1.5 and 7 ppm of ammonia and above 6 ppm of BOD, and high turbidity and high suspended solids. The water requirement was if the inlet was below 2 ppm, then you should result in less than 0.1 ppm of ammonia. If the inlet was between above 2 ppm, between 2 and 7, then 90% removal was expected. And the Filtralite managed all the requirements and with satisfaction. So it solved the problem. Another case study here, removal of manganese in Sweden, Olofström. You see that the inlet value here of ammonia is removed. And in this axis here, you see the dates. And this is a point that I wanted to point out, and that the removal of manganese, it takes quite long time. So first, after 4 months in operation, it will function. And this is very important to notice, that when you start to try to remove ammonia, it is fully possible to remove ammonia, iron, and manganese in the same reactor, but the manganese takes maybe 4 months to be in fully operation. In another case in Taipo in Hong Kong, Filtralite decreased manganese with 75% and ammonia with about 80–90%. And it also resulted in drastically reduced need for chemical additives. So if we sum up this, the efficiency of biofiltration process has a great dependency on the carrier properties. Filtralite offers a large porosity, which makes all this possible. Large surface for biofilm growth. High void volume, which means lower head loss and much better storage capacity, retention capacity. Longer filter runs is achieved due to the large void volume. This light density makes easy installation, affordable transport, but also very affordable backwash. And of course, if you design a new system, you can achieve less investments due to smaller pumps needed when the material is light. High resistance to abrasion give a long-lasting lifetime, which can be proven with a 30-year-old plant. Excellent surface properties and neutral pH will guarantee biofilm growth and addition, and biofilters can operate at high filtration rate up to 20 meters per hour, which is more than twice of a typical sand and anthracite in best case. So it's a lot of details for this, and what I want to say is that if any of you are interested in learning more about Filtralite and even testing it, I would be very pleased if you call in Mohammed and me for Teams meetings, and we can go more into details and discuss more about each and one's problem and see if we are able to solve it with Filtralite. And this was all for me. Thank you very much for listening.